Greetings, everybody. I'm back again to give you guys some help with Unit 4. So Lab 7 is all about the relationship between the Sun and the Earth system, and the question is how much solar energy reaches the Earth's surface each year. So the best way to start off these questions is to try to get your concepts down, and to wrap your head around it, I always recommend drawing a picture. So we can do a rough sketch of the Earth and Sun system. And so this is definitely not to scale, but it'll help us get our concepts right. The Sun is obviously much, 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 much larger than Earth. I forget the exact figures for that, but I do know the distance from the Sun to the Earth is about 150 million kilometers. So the Earth is extremely far away from the Sun, which is pretty amazing because you step outside, especially in Phoenix, you'll step outside, it might be 95 degrees, and when you realize that it can actually be hot outside when something that far away, you really start to appreciate how much energy the Sun actually gives off. So the Sun over here is constantly giving off light towards Earth, and since Earth is a sphere, the geometry of this system tells us that Earth is always half illuminated. So one side of the sphere of Earth is always in daylight, or it's in light provided by the Sun, and the other half is in darkness or night. And so the first question is estimate the surface area of the Earth facing the Sun in meters squared. So always remember to get your units right, and remember meters squared that comes about from calculating area. And for instance, the area of a square, one side is let's say such and such meters long, the other side is such and such meters long. Meters times meters equals meters squared. So we talked a little bit about surface areas and volumes in previous labs, but just want you guys to keep that concept straight as far as your units are concerned. But remember, Earth is a sphere. So for this question, you can either calculate the surface area of a sphere using Earth as your sphere and then divide it in half, because remember, only half of Earth is facing the Sun, or you could treat the sunny side of Earth as sort of a flat plane and try to calculate it as if it were a square area facing the Sun. Whatever you think is easier or more practical for you. The next question is estimate how much power reaches the Earth's surface in watts. Remember, watts are the unit of power, equals watts. Next, estimate how much solar energy reaches the Earth per year in joules. And remember, each watt is equal to a joule per second. So that question is not asking for how many joules per second of solar energy reaches the Earth per year. It's asking for joules. So you'll have to use unit conversion to get rid of those seconds and just be left over with joules per year. Finally, what is the current annual world consumption of energy per year? For that question, you can go back to the civilization lab and try to get an idea of how much energy civilization uses. And then finally, what is the ratio of energy delivered by the Sun to the energy consumed by humans? So you're going to have to take that energy by Sun and see what ratio that is by Earth civilization. Okay, so the next lab is all about cells and the human body. So the first question is estimate the volume of one cell. If you look at those microscope pictures of cells, they oftentimes look amoeba-like with little feelers, nuclei, different things inside of them. So how the heck are you going to estimate the volume of that? Well, like any estimating problem, you want to take this strange shape and sort of just estimate what that shape would be like if it was a little bit more manageable. So I like to turn a weird shape into a cubic shape, or you could you can even take this shape and turn it into something like a sphere, and then estimate the volume using the radius of this sphere. So whatever floats your boat. I usually go with the rectangle method, but it's totally up to you guys. And then the next question, after you find the volume of a cell, and remember it's a big unit, it's meters squared, so for something this small, you're going to get a very, very small number for meters. I'm sorry, it's meters cubed. You're going to get a very small volume in meters cubed for the size of this tiny cell. Then estimate the volume of a typical human being in meters cubed. So, start out with your really simple stick figure human. Say, hey, what is the average human height? Like, let's just go with something big round number like 6 feet. Remember this, I'm using feet here, so you're gonna have to go to Google, maybe find out how much 6 feet translates into meters. And then same thing. You can kind of estimate the volume of a human by turning the human shape into a big cubic shape here. Wow, that's a terrible 3D representation. I'm going to focus here. Okay, I can do this. It's a little better. And then you can remember, find the width, the depth, and the height of this to get the volume. And finally, the last question is estimate the number of cells in a human body. So you found the volume of a cell, you find the volume of a human, of course, both approximations. How many of these guys can fit inside of this guy? Of course, if you're using cubes over here, it can be a lot easier to think about how many of these cubes can fit into this cube. Just conceptually, that can be easier, but it's totally cool if you calculate the area of a cell using more of a spheric shape, whatever floats your boat. So I hope this helps you guys. If you have any questions at all, please ask online in the hallway discussions, and all the best of luck to you guys as you try to go through these labs.